Hi Arya, this is a second version of this video which hopefully will actually be more successful than the first one. Alright, so trigonometric identities for integration. Basically, the whole principle here is to make sure that I thought I could change colour, don't know how to change colour, no. Right, that you remove powers at all costs. So the reason being is we really don't know how to integrate cos squared. As you said earlier, if we did, for example, let u equals cos of x, then we would know that du by dx is minus sine of x, and so dx would be equal to du on minus sine x. Well, okay, that then becomes u squared, which is nice, but by replacing dx with minus du on sine x, then I have a problem. I can't actually integrate it with respect to u because I still have that minus sine x. And unfortunately, in this situation, I can't get it to cancel. So there must be other ways of doing it. And in fact, there are. And it all comes around to this table here in your formula sheet. The ones you are going to use the most are going to be that one there, and cos 2x equals 2 cos x, 2 cos squared minus 1. So you're going to say how? Well, I can integrate things like cos 2x. I can integrate things like cos 3x and sine 4x, because so long as these things aren't squared, then we can use the standard idea of it becomes 1 over k times the integral of whatever it is. And if you don't fully get what I mean by that, you will do in a moment. So I am going to say that I'm going to use my formula, and I know that the cosine of 2x is equal to 2 cos squared x minus 1. I want to isolate the cos squared, so I'm going to add 1 to both sides to get cos 2x plus 1 is 2 cos squared x, and divide both sides by 2, and I'm going to end up with a half cos 2x plus a half equals cos squared x. So I'm actually going to reformat this to become, move the half outside from both of these, cosine 2x plus 1 dx. That is infinitely integratable. Okay, so in which case I'm going to get a half cos 2x. So sine goes to cos goes to minus sine. When I differentiate, and I always remember them backwards, so cos is going to go to sine. So that's going to become sine 2x on 2 plus a half will become x. And he says, making sure that that actually deletes. Where's my delete? There. Okay. And then square bracket plus c. And so I get 1/4 of the sine of 2x plus x on 2 plus c if it's not asking for an integral. So there we go. That's literally it. I've changed something that looks disgusting with a power to something that looks much nicer. Again, tan squared. Don't know how to integrate tan squared, but I do know that 1 plus tan squared x is sec squared x. So that would suggest that tan squared becomes equal to sec squared of x minus 1. So I can now replace tan squared with sec squared x minus 1 dx, and I know that because tan differentiates to sec squared must integrate to tan, and that actually becomes quite trivially. He says, again, doing that the wrong way. Let's delete that. Let's delete that as well. So that becomes square brackets tan x minus x plus c, and because I keep doing that, that's just tan x minus x plus c. If it wanted the differential of, because it wants the integral of, it doesn't say an integral of, that's it. See what we're doing here? Yep, hopefully that is easier. Now, PowerPoint won't go to the next screen. Again, use your formula sheet. The formula sheet is literally the source of truth here. So another one that you are going to use, and I forgot, is that one there. We know the sine of 2x is 2 sine x cos x. Well, hold on, that looks strangely familiar. I've got a sine 2x and a cos 2x. Now this x here is arbitrary. We can put anything we like in there as long as it's similar. So if I change all of my x's for 2x's, that becomes 2 times 2 sine 2x cos 2x is equal to the sine of, and in this situation, because that's now 2x, 2 lots of 2x becomes 4x. So if I now have a sine, half sine 4x becomes sine 2x cos x, cos 2x, sorry, I can now replace this and make it the integral of, move the half outside, the sine of 4x dx. I've turned something that looks disgusting into something a lot easier. Again, substituting here is not going to make any sense. It's not going to help us at all. So that's going to become a half, brackets, sine goes to cos, cos goes to, so sine goes to cos, cos goes to minus sine. It's going to be minus the cosine of 4x on 4 plus c, or minus 1/8. So cos 4x on 8 plus c. All right, fingers crossed I have that one correct. Sine goes to cos, cos goes to minus sine. There we go. What about this one? Cos to the power of x all to the power of 4. So cos x all to the power of 4. Well, actually, that's going to become cos squared x all squared dx. And you're going to say, well, how's that going to help me? Well, again, we already know that cos squared x can be written as a half cos 2x plus a half. So now that's going to become the integral of brackets 1/2 cos 2x plus a half all squared dx. Now, you're going to say, well, where do I go here? Because you got that squared. Well, actually square out the brackets. But the first thing I'm going to do is I'm going to take out a half from each of those. So cos 2x now plus 1 all squared dx. And then square that gives me 1/4 the integral of cos 2x plus 1 all squared dx. That now makes my life a little bit easier. I'm now going to square that out. I'm literally going to go cos 2x plus 1 multiplied by cos 2x plus 1. So we get 1/4 integral of cos squared 2x plus 2 cos 2x plus 1 dx. Well, that's nice and integratable. That's nice and integratable. Hold on a moment. That looks disgusting. But we can use this same formula as we've got up here. So we now know that the cos squared of 2x must be a half cos 4x plus a half. So that integral now gets even longer and becomes the integral of, did I miss a bracket there? I did. So cos squared of 2x now becomes a half cos 4x plus a half. So all I've done is replace this with this, then copy that down, plus 2 cos 2x plus 1 dx. Now obviously I've run out of room and no longer can I do that for you, but hopefully you now know that that in fact is nice and integratable. And so yeah, that's exactly how you would do that one. Now this is the last one. And again, you might think, oh, well, I can do the same thing. And yes, you sort of can, but it goes back to the first example. What I'm actually going to do is split sine cubed up into sine x, sine squared x, cos x dx. Now the reason being is, sorry, that's cos squared. I'm going to let u equals cos x. So that now becomes u squared. What do I do with sine squared? Oh, well, hold on a moment. I know that sine squared of x plus cos squared of x equals 1, or sine squared of x is equal to 1 minus cos squared of x. So that now becomes 1 minus, but cos squared I've already said is u squared. So there we go. Where do we get the dx from? Well, let's differentiate that. Du by dx becomes equal to sine goes to cos, cos goes to minus sine, so minus sine x. And so dx becomes du over minus sine x. Do you see why I'm happy with that? Because that's going to become du, and this minus sine x here is going to cancel with that sine x there to effectively leave me just the integral of that. So I can now integrate, what is it, u squared minus u to the 4 du, and I am done. All right, and don't forget, you would then substitute the u of cos x back in. Yeah, so there'll be u cubed on 3 minus u to the 5 on 5 plus c as my sort of side calculation, as it were, which would then give me cos cubed x on 3 minus cos 5. Sorry, Arya, I don't know what's going on here. Cos 5x on 5 plus c. Fingers crossed. That is in fact my right answer. And as I say, that is the end of this. Hopefully that has been useful for you, good sir. We'll run through the Heffernan stuff at another time.